Hi everyone, welcome back to the 20th lecture of Spatial Statistics and Spatial Econometrics. This lecture will be the last lecture in the series while we transition to tutorials on ArcGIS and R. And today's lecture will talk about two broad, concepts. One is the Lisa principle and spatial dependence test statistics called the Moran's-I statistic and the Geary-Seek statistic. And then finally, we will introduce a little bit of hypothesis testing in the spatial regression models, right? So to do a bit of, recap, we started out this course by looking at a lot of spatial data sources, including the popular ones that are being applied for various contexts. And then we spent some time in developing the idea of spatial dependence formally using the statistics like the variogram, the covariogram, and then we came on to this understanding of spatial interpolation, right? In this journey, we have also figured out the importance of spatial stationarity, without which none of the statistics that we have seen till now, including the regression modeling, makes sense if our data are spatially non-stationary, right? So I really encourage you that, going forward, as you apply these tools and, in your respective research problems or any type of setting that you apply them, you should give a very hard thought and look to your data and your context and worry about stationarity, right? If you think that you cannot perfectly argue out stationarity, but still you have some ideas of where, in what conditions, the data might be stationary or might not be stationary, those need to be seriously documented whenever you produce such results, right? In this journey, then we have looked at this idea of spatial regressions, and we made this transition from regressions as statistical tool to a causal inference tool, right? Therein, we mobilize this idea of reflection problem due to a seminal paper by Charles Mansky, right? And from there, we have then, seen Lou Cancelin's sort of a school of analysis using spatial weights and spatial weights matrices in order to conduct spatial regression analysis, to model spatial dependence through either errors, regression error terms, or as a mean outcome term in the regression model, right? Today, we are going to continue that line of thought, and we are going to look at these univariate statistics that you can look at, you can see them as a counterpart to the variogram model or the covariogram model, and think of them as an alternative to detecting spatial autocorrelation in data, right? The fundamental difference between a variogram and a statistic, for example, on your screen, you're looking at this name called the Moran's-I statistic, which is a popular statistic to detect, spatial autocorrelation, is the dependence on your weights matrix, right? The dependence on a row standardized weights matrix is what differentiates the Moran's-I statistic or the Geary-Seek statistic from what we looked at, the variogram statistic, which is a fundamental, tool in order to document, detect, measure spatial dependence in data, right? So let's begin. So we are going to talk about detecting local spatial autocorrelation based on neighborhood weights in the first part of this lecture. And here, this lecture can be seen as divided into three broad parts. The first is called as the Lisa principle. Lisa is an abbreviation for local indicators of spatial association, and we will go over this in detail in a minute. And then we will look at two popular statistics called the Moran's-I statistic and the Geary-Seek statistic, right? I will just write out the overall aim of this part, of lecture 20. So here, the first aim is to identify location of spatial clusters. Okay, and the second is to assess the extent or degree of spatial autocorrelation in data and comment upon the statistical significance properties. Right? I mean, statistical significance of what? Of the measure of a degree of spatial autocorrelation. That is going to be either the Moran's-I statistic or the Gear-EC statistic. Okay. So the first thing first, we are going to talk about the Lisa principle, right? So Lisa principle. Okay. As remarked earlier, Lisa is short form for local indicators of spatial association. Okay. Now, they deliver a local spatial statistic for each location. So we can say location based, spatial statistics. So I'm going to say that I'm going to modify my last sentence and make it a little bit more concise. I'm going to say they provide us with location specific spatial statistics. All right. And the sum of these location based statistics, right? Sum of these location based, I'm going to say Lisa statistics, provides a measure of global spatial dependence, or spatial autocorrelation in data. Okay, so we are trying to make a comment upon global, provide a global statistic. But when we do that, we are going to somehow, through this Lisa principle, we are going to have these location-based spatial dependent statistics that we will then aggregate over space. And this link between local and global, statistical understanding of spatial autocorrelation is where this Lisa principle is situated. So by Lisa principle, we will be able to say that the global statistic, when I say global statistic, I mean global statistic for, spatial autocorrelation is going to be equal to k times, k is a constant, times summation of, let's say, Lisa I. So a statistic that we evaluate, you can say a component, a local statistic at location I, right? So local meaning location I based, right? Local statistic for spatial autocorrelation. So we'll be working with these location based statistics. We are going to fundamentally define location based statistics, and then we are going to define them in a way so that we can then sort of aggregate them with a constant, multiplier and, formalize a global, statistic. Okay. So that's about the Lisa principle. And now two popular statistics based on this principle are the Moran's-I statistic and the Gear-EC statistic. Now, Moran's-I is a more, recent statistic, more popular statistic. So I'm going to spend a little bit more time on that and, give you just a gist of the Gear-EC statistic, which is based on the same principle. So what we discussed for Moran's I will also, quite a bit of it will apply for Gary's C, but we will also see how they are different and some broad introductory details. Okay, so the Moran's I statistic, if you want to read more about it, as I said, it is based on spatial weights. So it comes from the Luke Anselin school of thought, right? So Luke Anselin was, has pioneered this idea of using spatial weights for or a weights matrix based, measure or measurement of spatial autocorrelation, be it for finding a global statistic that we will see now, or for modeling through spatial regressions that we have seen in the past, couple of lectures, right? Okay, so the Moran's I statistic, it is based on, let's say two, components. Okay, so two fundamental components of the Moran's I statistic is first a row standardized weights, that is Wij, something that we have seen now, and by consequence you can say and a weights matrix. Okay, a weights matrix, I'm going to say W tilde because previously we saw W is a weights matrix which has a binary 0, 1 characterization between whether the row representation I are neighbors with column representations J, and the row standardization basically normalized for the degree of interconnectedness for these spatial units, right? So we are talking about row standardized weights and a weights matrix entering these the Moran's I statistic. Now I'm using, when I'm introducing, I'm saying W tilde, but as I go forward, just for just for clarity, if I use W, I'm basically talking about row standardized weights. I'm never going to talk about non-row standardized weights. And why is that problematic? For that, we have to go back to previous lectures and then figure that out. Okay. So second is, the second component is the deviation from mean. That's simple, right? So I'm going to say this is Zi, right? So deviation from the mean and a spatial weight are two components that comprise, a Moran's I statistic. Then Moran's I at location small I, okay, is denoted as under. Okay, so I have I at location I. So capital I represents Moran's I. Then at location I is equal to summation J Wij, I'm saying tilde, so weight, row standardized weight, Zj Zi divided by I Zi squared. Okay, and of course this location I represents, let's say if I had a domain of interest D, right? If I have a domain of interest D, and every location, if it's a geostatistical domain, then I know that every location here is a representation of I, right? So if I have a data set which goes from I to 1 to n, then I is defined for all those locations, right? Now given that Zi is or represents, let's say represents deviation from mean, we have something like an underlying process X such that Zi equals Xi minus X bar, right? So that is what deviation from mean really means. And so I can rewrite II as summation J Wij Xi minus X bar Xj minus X bar divided by summation I Xi minus X bar the whole squared. Okay, and I'm again going to say wij is equal is a tilde. So you know we have this entity. Okay, now if you just stop for a minute and pay attention, you know, draw your attention to this last you know, expression for II. If we did not have the weights wij, right, the numerator is a representation for covariance between, you know, x at location I and location j. And in a denominator, I am basically normalizing it with the variance of xi's, right? So I am in a way writing a correlation metric, right? So a correlation would have been rho summation x minus. So if you think about the traditional covariance correlation you know metric, then you have you know, rho xy will be summation x minus x bar y minus y bar divided by summation x minus x bar squared and y minus y bar squared and the whole thing square root. When we brought this to the spatial setting and we defined what was called as the correlogram, right? In that scenario, you know, so if I say rho spatial, you can go back and look at the correlogram. There it was C xy over C 0, right? Now, if I remove the weights, all I'm looking at is a correlation metric, right? A correlation, a traditional correlation metric enhanced by spatial weights is the Moran's-I statistic. Okay, it's as you know, starkly similar as that. Okay, so let's, with that thought, you know, develop this you know, concept further. So note, okay, so again notes, we have said this now. You know, xi, I'm going to rewrite the Moran's-I statistic for clarity. Let's rewrite it on this page and then move forward. So I have II, I'm just writing this out from the previous slide, summation j wij tilde xi minus x bar xj minus x bar divided by summation I xi minus x bar the whole squared. Okay, now you know, notes xi minus x bar in the numerator. Okay, so I'm talking about this term here, right? Xi minus x bar in the numerator can be taken out of the summation operator. Right? Why is that? Because the summation is over j. The summation is over j. So with respect to j, xi is a constant. So I don't really sum xi. Once I fix a location I, xi minus x bar is a constant. Right? So that means this term can come right out of the summation operator. Right? And if you look at the numerator, it is itself a constant. It's just you know, a variation, you know, sample variance times n minus 1. Right? So denominator is a constant because it doesn't depend on I. You are, you know, integrating I out of the denominator. Right? So I'm going to say that. So the first note was that. The second note is the denominator is a constant. Right? That is what I'm trying to say is that it does not depend on I. Not very hard to see. Right? So now we will rewrite our Moran's-I as xi minus x bar divided by summation over I xi minus x bar the whole squared times summation j wij tilde xj minus x bar. Okay, this can be then further written as xi minus x bar is zi, that's the deviation from the mean, summation over I zi squared summation j wij tilde zj. Okay. Now clearly this term sitting outside the summation j term is a constant, right? We can say a constant a. So then I can write this term as a times summation j wij tilde zj, right? And as I've mentioned earlier, the Lisa principle, right? I apply the Lisa principle. I will now link the local statistic with a global statistic. Okay, so let me do that. So I'm going to say summation I will be equal to n times I, can be seen as a ni. Okay, so as if I am summing n times i's, at each location. So if the local correlation was a constant at each location, I can think about a global average being capital I, and n times that local global average is going to give me the sum of each individual unit, providing me a correlation spatial correlation metric, that is the Moran's I. So this would mean that I can be written as summation I over n, and this I is termed as the global Moran's I statistic. Okay, and clearly the global Moran's I statistic is an average of the local Moran's I statistics evaluated at locations I in our sample data. Okay, so now we have sort of developed this global idea of a global spatial autocorrelation metric, that is the global Moran's I. And of course, once I have a statistic, the next step for me is, okay, what about statistical inference? What about the confidence intervals on this statistic? Okay, so that's the next natural step. The next natural step is inference on or for the Moran's I statistic. Okay, the inference for the Moran's I statistic. So I have I, which is equal to xi minus x bar over summation I xi minus x bar the whole squared summation j wij xj minus x bar. Okay, now the next step is to define a z score. I'm going to say zi score, right? So z score is for constructing the 95% confidence intervals, because it's z for every I, because I'm looking at Moran's I at location I. I'm calling it zi score for the local Moran's I statistic II. Zi is going to be equal to II minus expectation of II divided by the standard deviation of II, that is the variance of II square root. Okay, now this is a standard definition for any statistic for which we want to conduct statistical inference. The question is, how do we construct these entities, expectation II, where do these come from, right? So to construct them, we have a computational module, right? So I'm going to say expectation of II and the variance of II are computationally evaluated. Okay, so there are several steps. So I'm going to go over these steps. The first step is to hold value or location fixed at location I. So I have a data set. Okay, I have a data set. Here is my data set. Okay, there are the locations I, J, K, L. So these are the locations for which I have data observed over an irregular lattice. Okay, so the data are, you know, irregularly spaced and all that. And each location that I observe the data can be thought of as location I. So I'm going to go at, so for example, if these were groundwater values, then at every I, I'm going to observe groundwater values. Okay, so what I'm going to do is I'm going to go at location I and I'm going to fix the value of groundwater level at that location. That's step one. What's step two? Step two is randomly permutate or permute remaining n minus 1 values, right? What does it mean, random permute n minus 1 values? So I have fixed the value at location I, right? For all other locations, I'm going to now randomly assign the values for the remaining n minus 1 values. So I have my bag of n values, right, at different locations. I'm going to pick one and hold it constant. The remaining n minus 1 in my bag, I'm going to randomly assign them to all the other locations. Okay, so it's kind of a Monte Carlo, right? So it's a simulation. That is what I'm trying to do, right? So say I have a sequence of values, you know, 2, 4, 6, 8, and 10. Let's say I have data for 5 locations, and this is the bag of values I have, right? Let's say I go to location 3 and I fix the value at 6. Okay, so I go to location 3 and I fixed my value at 6. Now for the remaining, I have values 2, 4, 8, and 10 sitting in a separate bag. These are the ones that I have not fixed. I have not held them fixed. So what I'm going to do is now with replacement, I'm going to randomly just assign these values at different locations. Okay, I'm somehow simulating a process of generating the data. Okay, let's say this is one, you know, such construction. With this new data set, you know, now with the new sort of, you know, spatial setting, what I'm going to do is I'm going to compute II. Okay, so I'm going to compute II. And now this activity I will do for every location I. Okay, for every location I go in, I hold the value fixed, and then I, randomly assign the remaining values to all other locations, and then I compute my II, right? For each permutation, and each permutation basically means location, because the permutation is tied to location, right? So when every time I permute, I'm basically at a location I plus 1, I minus 1, I plus 2, and so on and so forth. Okay. Now, third step is to repeat steps 1 and 2. Steps 1 and 2. So I'm going to say 1, 2, 3 many times. I'm going to say m equals 500 times. Let's say I repeat these steps 500 times. I've really simulated the process of spatial construction in the data in every possible way, right? And as step 4, I will get the mean and standard deviation of IIs drawn from 500 iterations. Okay, the set of IIs now I have for each of these iterations. I'm going to collect them, get the mean value, get the standard deviation, right? And also I can draw confidence intervals equals, in terms of the 5th and the 95th percentile values. All right. So basically what I've done is that I've gotten this mean. This mean relates to this expectation II. The standard deviation here relates to this variance of II square root, right? But I've not gotten to them analytically, rather I've gotten them computationally or by using simulations, right? Now, all of this is done on the software. We don't really do it. And in the next module, we are going to actually transition and start doing these things, right? What is important is to know what the software is doing behind the scenes, so that if we see some results which are, which we feel are, something that we didn't expect, then we can at least try and address those things. Okay. So the output on, ArcMap or ArcGIS, something that we are going to start as the next module after this lecture, is going to sort of provide me what is called as a cluster and outlier analysis of Moran's I based on a 5-color scheme. Okay, it's basically going to give me, once I calculate Moran's I, the output will have a 5-color scheme, right? And that scheme will have 5 categories basically in different colors, which says, it will say not significant, high, high, low, low, high, and the next you can guess is the low, low category, right? And it will say, when it says high, high and low, low, it's going to call it a cluster that agrees with positive spatial correlation of nearby values, right? And high, low and low high are going to be, identified as outliers, and some of those are going to be not statistically significant. So the Moran's I globally is not going to provide me, I have a global statistic, but locally you may not have spatial correlation, spatial dependence in data in some regions, and you may have it for other regions, right? So this kind of distinction is directly, feeding, I will say feeds directly into the tutorials on ArcGIS. Okay, and last thing I want to talk about in this part of the lecture is the Geary's C statistic. Now, the Geary's C statistic, looks pretty similar, by the way, to the Moran's I statistic. It's given by n-1, capital N is the size of the data, summation I, summation j. So instead of just summation j, we have summation I and j. Row standardized weights, xi minus x bar the whole square divided by 2 summation j, wij summation I, xi minus x bar the whole squared. Okay. Now, we know that wii is equal to 0 for every I, right? And the interpretation, I'm going to provide the interpretation here, is that Geary's C is inversely proportional or proportional to Moran's I. So that means if Moran's I provides a signal of a positive correlation, then Geary's C is going to provide a, a lower value. So if Moran's I is higher, Geary's C is going to be lower, right? Ci is always greater than 0, but it is unbounded on the higher side, right? So it can, technically go to infinity. When Ci is less than 1, that is to say that Ci is between 0 and 1, then it represents increasing positive spatial autocorrelation positive increasing spatial order correlation as Ci is decreasing. And whenever Ci is greater than 1, right, that means, Ci is more than 1 and okay, then it will represent situation of increasing negative spatial order correlation as Ci is increasing. All right. So as Ci basically increases overall, you can think about it as a measure of decreasing positive spatial order correlation. And in fact, when Ci is greater than 1, you can think of that situation as a as one of negative spatial order correlation. Okay. Some notes of caution. Okay. First, both Moran's I and Geary's C are exploratory statistics. Okay. We can at best talk about correlations. We can't really talk about causation. We can't say that an entity in a neighborhood is causing behavior at the location of interest. No, they are just associated. So they are merely explorations. And both these statistics assume that the underlying processes are same. So that is, they assume stationarity. Okay. Assume stationarity. And the way sort of this has been interpreted is that they assume that a given data set is in a spatial equilibrium. So in a way that there is no transitory processes in the underlying data that we are looking at. So we are looking at land use transitions, then this statistic can be problematic. Okay. And finally, something that I've already said is that these statistics are strictly univariate, right? So they are univariate only, they have no utility in multivariate analysis that you've already seen with spatial regressions. Okay. So with that, this is an introduction of the Moran's I mainly. I've given you some notes of Geary's C. Moran's I is sufficient for our purposes in this course and for most applications, and it's a far more popular statistic today. It's based on the spatial weights. So if you don't have a definition of spatial weights, you can't really get to a Moran's I, right? And I'm ending this lecture at this part of the lecture with a caution, some cautionary notes. And I want to sort of drive a point home that, we have more sophisticated tools at our disposal in terms of the variogram models in order to infer upon spatial order correlation. So perhaps even though this tool is available, perhaps we have a more advanced or fundamental understanding of how to measure spatial order correlation for very sophisticated, surfaces. Okay. With that, I'm going to end this part of the first part of lecture 20. We'll have a very short second part where we'll introduce hypothesis testing for spatial regression models, and then we'll move right on to the tutorial. So thank you very much for your attention.